Greetings everyone, welcome back into Calc 2. Time to continue into this next third unit of Calculus 2 where we're talking about curves and functions in space. And to really start off the more generic structure, we have today's lesson on parametric equations. And the idea of parametric equations is that I want to be able to make a more general version of the idea of what a function is for us. In college algebra or maybe in high school or wherever it is that you first heard about functions, they probably defined for you a function as a connection between two sets where you have the domain, which is the inputs, the range, which is the outputs, and the domain points to the range, point for point. And to further restrict functions, to make it what we call a function, all of the items in the domain can only be used once in any pairing with a range. Okay, so that limits a lot of the functions that we were able to study, especially in your first round of calculus. Okay, getting through to this next stage of calculus and building up into multivariable, where you need to be able to go in any direction and draw any kind of curve necessary, we need to generalize this idea of functions. And parametric equations is going to be that nice alternative for us that we need. The idea behind parametric equations is that I no longer treat x strictly as an independent and y strictly as a dependent. They're not necessarily going to have a direct connection to each other, although they really are still going to be connected to each other. Okay? What we do is we take something called a parameter, which is another variable that you don't see in the reality of x and y. A good example of this in our real everyday lives would be time. It's a variable that is always proceeding in value, but we don't always see it in our everyday interactions, but it is still moving onward and making a conception of some sort of line of values. Okay, that's what a parameter is here. I'm basically going to take some function, used to be y equals f of x, and I'm going to take the y and x variables and redefine them as each a function of some parameter t. So I still am going to have the connection between x and y. It's just got a middleman, if you will, a middleman through t. Okay? So in the old school version of functions, we think of x causing y, so to speak. Maybe you never thought it in quite that many terms, but if you think about it, that's sort of like the way we always looked at it. X was the input, y was the output. X has to be restricted because it has sort of a cause and effect sort of following. You plug in an x, it calculates a y. Okay, now in parametric equations, we basically pick a value for the parameter t, and then that gives us an x and y value directly. So basically what I'm doing is I'm going to take the same curve we would have had in the original function. It's going to graph to all of the same points, but it's going to have a different way of calculating them. It's also going to have possibly a different direction of drawing. It could have all sorts of more generic ways of thinking of that actual curve. And it will also make it to where x no longer needs to be restricted in situations where we think we don't have a function. Because now t is my input parameter. And since t doesn't actually exist on our graphing grid, then I can restrict or not restrict t all I want, and I can still have whatever shape I desire on my grid. Okay? So here's an example of a parametric equation. Imagine I have the function y equals x squared. Okay? But I'm going to restrict its domain to only 0 to infinity, and 0 is not included. And that is, I'm saying, synonymous with the parametric equations where x is equal to e to the negative t and y is equal to e to the negative 2t. Now I want you to notice that I could use substitution here. This 2 in the negative 2t, I could actually bring that out, and this would be e to the negative t quantity squared, right? Which x is equal to e to the negative t. So it's just like I'm saying whatever x value is that and squared, right? Because that's basically the relationship here. So you can see this is going to be a y equals x squared setup. However, x and y are being controlled externally through t by me picking values of t. Both of these functions, okay, both of these setups are going to graph to the same shape. They're both going to graph to this parabola where the bottom vertex point here has been cut out and not let to be equal. Okay? Typically, with y equals x squared, you would pick x values like 1, 2, 3, and you would plug them into calculate y. 1 squared is 1, 2 squared is 4, 3 squared is 9. And so you get the points, just in the normal fashion. Okay? There's no actual connotation to a direction or anything like that, except typically x is, we like to count up, but we don't always have to. Okay? With the parametric equation, I actually have a connotation of a flow or a direction of the way that this path should be walked. T is an external variable, and t has its own way of counting, right? It has its own number line that's somewhere else, not in my graph. And if we think of t as time, like it's going to move forward, okay, then that causes x and y to be calculated in a certain order. Okay, now here's what I mean. If you were to do these points over here, old school, remember typically we would graph from left to right and it would go this way. Notice, even though this is going to graph to that same shape, the points right here show me this. If I plug in t equals 0, I get the point 1, 1, which is here. Right? So this is t equals 0, right here. If I plug in t equals 1, I get 0.37, and y is 0.14. That's this way. This is t equals 1 right here. Where's t equals 2? It's 0.14, and 0.02, it's really far down here. Right? This is where t equals 2 is. When t is negative 1, right, I plug in and I'm just getting e, right, because e to the 1, and then I'm getting e squared. So t equals negative 1 is more like up here. That's t equals negative 1. T equals negative 2, I'm at 7 and 54. T equals negative 2 is already way off of the graph that I've drawn here. I know I didn't even really put a scale, but if you think about it, t equals 2, it's skyrocketed. Okay? So here's the thing. When you do this old school, it just follows the parabola, evenly, because you do your x's evenly. Here, there's more than just the points. There's also what is controlling it. These calculations right here are exponential. So there's going to be a certain area where these things are really close together because it's shrinking. And then there's going to be a region where it starts leaping in huge bounds because that's what exponentials do. And as you can see, that already started to happen here. T equals negative 2 is way out there off of my graph here. Also, if you think about the way t is enumerated, t0, t1, t2, then the flow of this graph is actually this way. The flow of this graph is this way, like this. Okay? So Parametric Equations has several new pieces of information that we weren't even thinking about before that we can still use to our advantage here. Like the fact that these points graph to a certain path is immaterial to the way that they walk on them, right? It's some sort of independent controller here. Here's another thing you need to think about. A parametric equation is not unique to its curve. It's unique in the way it walks on the curve, right? The direction that it's going can be changed. I could take the negatives off of here and it would actually walk in the other direction, right? It would actually flow the other way. But even the way it is, the curve itself is not unique, okay? There are an infinite number of other parametric equations that I could all make graph to y equals x squared. Pick any function you want. Let x be equal to tangent of t. And then just let y equal to tangent squared of t. And that's it. That parametric equation will graph to the shape y equals x squared. But it'll do it in that sense more along the way a tangent would dictate the flow along the curve. Okay, so parametric equations are more than just the curve now. I'm able to have this other inside information that talks about what's going on that curve, and I can apply it to many different other things rather than just graphing. All right, it can be connected to energy and to motion and to fields and all these other things. And this is the generalization of what a function is going to be. Not just the curve itself, but what can we do inside and control the points on the curve and how I use the points on a curve. Okay? So just remember, a parametric equation is not unique as far as the curve that it's connected to. I could make any parametric equation that we desire connect to some curve. You just have to design the x and y equations correctly. Okay? Here's a couple of more examples. Create equations for a line segment between -3, 5, and 10, -1. Okay? Now, old school, this would be some sort of y equals mx plus b, right? Here, we're going to have x is equal to something, y is equal to something, and I don't even want the whole line this time. So I won't have to restrict x and y. I'll simply have to restrict my t value so that it goes between those 2 points. Okay? So here's what I'm going to do. I'm going to create the equation of the line by selecting one of the points as a start and the other point as a finish. Okay? So here's what I'm going to do. I'm going to say when t equals 0, I know that I want x to be -3 and I want y to be 5. So it's like a starting point. Pick any other number you want. Typically, people pick 1. Okay? When t equals 1, what do I want? I want x to be 10, and I want y to be -1. So now what I need to do is just come up with some equations that make that happen. The easiest way is to use linear equations to make a linear equation. Do I have to do that? No. I'll show you an example of that in a second. But let's go the easy route first. Let's do the most basic, because that's usually the most powerful, right? Keep it simple. So here's what I do. I'm going to say that I want x to be equal to -3, right? The starting point. And then it needs to go up to 10 whenever I plug in t equals 1. Well, how far is it from -3 to +10? It would be +13, right? But I don't want to add that 13 when t is 0, and I do want to add that 13 when t is 1. So what I do is I multiply the 13 by t. Okay? So when t is 0, it doesn't exist. And when t is 1, I get all of the 13 and only the 13. And now I'll do the same thing with y. Y is equal to, start at 5, and then I'm going to say, how do I get to -1? That would be -6. But I only want to do that when t is equal to 1. So I'll say times t. Okay, so then this set of equations right here actually is the set of equations for the line that goes through these 2 points. Okay, now how do I guarantee that it's just the segment? Well, if I pick this as the start and I pick this as the point after it, all I need to do is say beginning t value is the beginning of my interval and ending t value is the end of my interval. So in other words, I'll say t exists on 0 to 1. And then that is the equation of the segment right there. Okay? And which way does it flow? You can already figure that out. I picked a beginning and an ending point, right? When t is 0, I'm at negative 3, 5. And when t is 1, I'm at 10, negative 1. So the flow is this way. Could I have made the flow the other way? Absolutely. How would I have done that? I would have put t equals 0 for this point and t equals 1 for this point. I could still make it linear. It would just flip-flop some of the signs and change a few numbers, and it would still be the exact same segment. But then the points would actually enumerate in the other direction. Okay? Did I have to use linear? Did I have to pick t to the 1? Nope. Think about it this way. I could also have picked any other polynomial simple term, because the any power, 0 to any power is still 0 and 1 to any power is still 1. So I could have said t to the 5th if I wanted to, as long as I did it to both of them the same. Okay? I want the relationship to be the same between x and y to make it a linear, but I could have picked t to the 5th, and notice it would still graph to the same thing. But what would be different? Since it's t to the 5th, you'd have an uneven flow. It would still flow in this direction, but they would be wider at first, and then they would start shrinking up at certain points. It would be more points gummed up in one spot, and the points would start to spread out if you just plugged in like t equals 0.1, t equals 0.2, t equals 0.3. That would be the only difference that you would see. They would be like this, right? They're bunched up in certain spots and then start to spread out, because t to the 5th grows faster than just t. So it's like controlling it externally. But again, I could have picked anything. I could even have picked logarithms. The only difference with logarithms, if I wanted to put ln of t here, I can't do 0. I would have to pick 1, because ln of 1 is 0, right? And then I would have to pick some other value of ln, like e, right, to get the 1 that I want. So I could have put ln of t, ln of t. It would have just changed my interval a little bit. And again, it still would graph to that line. But what would be different would be the flow. I could change the direction if I wanted to. I could change the way that it's grouped depending on which object I choose to control it with. Okay? So because it's just a flowing line like this, it has a lot of different options that don't vary very much from the original equations. Now, what if I want to put this back into our normal rectangular form, is what we would call it, right? If I want to convert this back, we do what's called eliminating the parameter. To eliminate the parameter, all I would do is solve for t. In this case, there's different methods for different things. I'm going to show you that in the next example. But in this example, t is pretty simple. If I just solve for t in one of them, I could substitute it into the other equation, right? So for example, to eliminate the parameter, I would say right here, x equals negative 3 plus 13t. So x plus 3 equals 13t. Divide both sides by 13, I would have x plus 3 over 13 equals t, right? And then plug that into the y. Y is equal to 5 minus 6 times x plus 3 over 13, like this. And then, of course, you would do all of your normal simplifications and whatnot from there. Y equals 5 minus 6/13 x plus, oh no, minus 18/13, right? Because I just distribute the -6 in here. And then 5 is really 65/13. So then 65 minus the 18/13, I would get y is equal to -6/13 x plus 55 minus 8 is going to be 50 minus 3, 47/13. And this is your typical y equals mx plus b right here, right? And if you plug that in, or if you graph it out, you'll notice you'll still get this same thing. However, because I didn't restrict this one, this is going to tend to be the whole line, right? I would actually have to find that, well, I already know the x values, right? When x is -3 or when x is 10. Right? You plug in x is -3 and add these up, you'll get 5. And plug in x equals 10, right? Same thing, you'll get the -1. Okay? Notice the slope is negative as it should be, right? And it's actually the slope you would have calculated anyway. If I do 5 minus -1, I get 6 over -3 minus 10 is -13, right? -6 over 13x. Okay? But this equation right here is easier to plug in and get values of x and y. Think about it. Versus this with the fractions, it'd be much easier to plug in values of t here, even if they were decimals. Also, I would get better control of where I am on the line by gauging where t is. And if I really wanted to, I could reverse the flow. I could talk about just this one section much more easily. Parametric equations gives us a lot of different options that we didn't have before. Okay? Here's another example. Eliminate the parameter to discover the modeled function. Now up here, I eliminated a parameter just by substituting, and sometimes that works. But other times, there are things just a little too complicated that you may not want to substitute. So right here, for example, notice both of them are trig functions. If I try to do a direct substitution, I'm going to have to solve here, which is going to give me an inverse sine. And then I would have to plug that into the other one, which means I would have a cosine with some complicated inverse sine statement. That would be a yuck monster city. Okay? I wouldn't want to mess with that. In fact, when it comes to the trig type of things, or logarithm and exponential, right? Even those, they have their own set of laws. Trigonometry has all its identities. Try to think of some of those that might match up what we're doing here. In this case, I know that sine squared t plus cosine squared t is equal to 1. So what I would want to do first is actually just isolate the cosine t and the sine t, just those two. Okay? So that's what I'm going to do first. I'm going to notice that x is equal to 2 cosine t plus 1. If I subtract the 1, I'll have x minus 1 equals 2 cosine t. And then divide by 2, I'll have x minus 1 over 2 is equal to cosine t. All right, and likewise, I'll do the same thing with the y variable. I'll solve for sine by adding the 4 and dividing the 3. So that's going to give me y plus 4 over 3 is equal to sine of t. So I didn't bother doing the inverse trig because I know that there's a relationship between cosine t and sine t. And now I'm going to use that relationship to my advantage. So right here I know that cosine squared of t plus sine squared of t is equal to 1. Well, cosine of t is x minus 1 over 2, and then it's squared. So that would be this, x minus 1 over 2 squared plus sine of t is y plus 4 over 3. Y plus 4 divided by 3 squared is equal to 1. If I write this another way, it would look like this. X minus 1 squared over 9 plus y plus 4 squared over, whoops, 2 squared is not 9, sorry, 4. 3 squared is 9 equals 1. And here's my equation. I'm hoping that you recognize that after just coming off of the last lecture on conic sections. That's an ellipse where it's centered at 1, negative 4, and it has major axis in the y direction of 3 and minor axis in the x direction of 2. Okay? So that ellipse is just like the ones that we graphed in the last lecture. But notice, in this particular parametric form, it may not be necessarily 100% easier to see the x and y points, but it actually is a different way to understand them. Right here, cosine t and sine t are circular functions. And notice it goes from 0 to 2 pi. It's like taking that ellipse and drawing it in a path that would be more of like a going around the pathway instead of thinking of it as x values and y values, you know, cold and blocky like this. So if I actually graph this thing out, right, it's going to be centered at 1, negative 4. So 1, negative 4 would be here. And then it has major axes of 3 up and down. So that would be like here and here. And minor axis of 2, that would be like here and here. Okay, so the actual curve would look like this. Something like this. Give or take. But if you consider the way this is done, x is cosine t, which is actually typical trig. Cosine is the adjacent, right? The x. Sine is the opposite, the y. Okay? It's actually flowing in the direction of a normal angle. This way. Like this. Okay? Here's another way that you can tell that the flow is going in that direction. Plug in a few t values that are easy and quick for you to know. For example, when t equals 0, right? Cosine of 0 is 1. Sine of 0 is 0. I'm going to get x is equal to 2 times 1 plus 1, 3. 3 times 0 is 0 minus 4. Y equals negative 4. Okay? So 3, negative 4 is this point right here. This is t equals 0. That should sort of make sense. If this had an x and y axis, right, that's the beginning of a standard angle on the right side of the x-axis, and then it flows this way. Okay? Pick another point, like t equals pi over 2, 90 degrees, right? Well, if it's 90 degrees, shouldn't it give me this top point? Calculate it. Cosine of 90, cosine of pi over 2 is 0. I'm going to get x equals 1. Sine of 90 is 1. 3 times 1 minus 4 gives me negative 1. That's this point right here. That's going to be t equals pi over 2. So you notice the flow is going that way. And it's just like a trigonometric relationship would be graphed with the angles. It's flowing like a normal angular direction. So this is another way of understanding the points on an ellipse in a completely different fashion and actually giving them a particular direction of flow. Okay? So this is another example of what a parametric equation can do. Not just with equations, it can actually make it seem like it's an entirely different system. Let's get a few more examples of these guys and eliminating parameters. All right, so let's take a look at these first few shapes that we have here. I'm going to click on this guy here. And let's see. I've already typed in this one for you so we can sort of get a feel for the way things are going to go here. Notice that after I've put in the x and y functions here, it automatically gave me the graph for it, right? But also, notice it is exactly the graph we were talking about. It doesn't have the other half of the parabola. For example, if I type in y equals x squared, you can see normally it would want to give me the whole graph for that. But our guy here is just this half right here. And in fact, the values, I want to squish down and get a bunch more of the values here so you can get an idea. Okay. And what I have is a point on the graph here. And I have it connected to a t variable that's going to increase. So take a look. As the t value increases towards 0, you notice that point came down pretty fast. And now it's ever so slightly just edging its way towards 0, 0. And it never quite makes it there. If I get all the way back to 0 here. Yeah, you can see right at 0 there, it was getting to that point 1, 1. Just right there. Right, it's approaching that, and then very, very quickly it shrinks on down. As t gets more positive, it gets closer to 0, 0. And eventually, by the naked eye, we can't even really see that anymore. All right. So let's turn that off for a second. And let me change the curve that I have here over to the other equation that we have, which is -3 plus 13t. -3 plus 13t. And 5 minus 6t. Okay, and then on top of that, we need to change our a and b values here. The beginning and ending of our domain, we said, was 0 to 1. So here's the actual curve, quote unquote, but you see it's a segment. And if I let t be 0, the point is up here, you see. And so if I tell it to go, notice that what it's doing is flowing along the line in the path towards the other endpoint. So that is the direction of the flow here. This point has the coordinates from that curve. And that is what the actual parametric equation is implying in one sense. That there is a flow to this curve, not just the points themselves, but the t values that are initiated in the background give it sort of a progression. Okay, and then the last one that we talked about, let me go ahead and turn off the graph there. The last one that we talked about there was 2 cosine t plus 1 and 3 sine t minus 4. And then our a and b values need to be 0 and 2 pi. Okay. So then I'll put my t at 0 here. There's our point. Here's the curve. Notice it's that ellipse that we were talking about, and the point is on the very right hand middle side. And if I tell this t value to now increase, notice it is going in the direction of a normal rotation, which is what we expect it to do. This is a circular take on the points given by this parametric equation. So the flow of this ellipse is in a counterclockwise direction from the standard position. Now that you've seen the basics, let's get a bunch more examples under our belts so that you can see just the variety and power behind this way of writing functions. So I've got some parametric equation examples here. I have x equals 4t squared plus 8 and y equals 3t plus 1. Now, whenever you're given a pair of parametric equations like this, and you don't see a listing of the domain for t, like we were in some of the other examples before, then it's pretty much just the assumed maximum amount of t values that are allowed. And a lot of times we try to make it where t can be any real number, or any value basically. Okay, so then right here, that's exactly what we're assuming. Since t is just being squared and multiplied and added, really t can be any number for this particular parametric equation. What we typically try to do is a couple of things. We really want to get a graph so that we can see what's going on, but also we want to know the direction of the flow, and eventually we'll be talking about in the calculus of the situation, like rates of change and things like that. That's the next lecture. Okay, so to get an idea of what this guy really is, I'm going to start by plugging in a few points and eliminating the parameter. And I don't always plug in the points first, and I don't always eliminate the parameter first. It's just whatever feels easiest. At this point right here, it looks pretty easy to eliminate the parameter. So I'm going to do that first. Okay, so here, notice that I've got the fact that t squared is going to be x minus 8 divided by 4. X minus 8 divided by 4 is equal to t squared here. Okay? And the next thing that I'm going to notice is that if I solve for t here, then I've got y minus 1 divided by 3 is equal to t. Okay, now sometimes it's all about just solving one of these things and plugging it into the other one. Okay, in this case, you could really go a couple of different ways with this. I can take this and substitute it in for t, or I can finish solving this and plug it into t over here. Okay, let's see what happens when I do it the more straightforward way of plugging this into t squared. Okay, if I do that, then I'm going to have x minus 8 over 4 is equal to y minus 1 squared over 9. Now, look at what I did right here, right? I took the y minus 1 over 3, and it's equal to t, so I plugged that into t here, and it squared everything. So I have y minus 1 squared, and then I have 3 squared, which is 9. Okay? I didn't bother multiplying out the y minus 1 squared because that seems like an easier way to leave it with just the completed square part. This might very well be something that I could, do some shifting with or whatever. To make it look more like something that you've most recently recognized, I'm going to multiply both sides by 9 now. When I do that, I have 9/4 times x minus 8 is equal to y minus 1 squared. Okay? So right here, notice this is exactly like the parabolas from the last lecture. I have one of the variables squared, and I have the other variable times some number. Now when y is squared, remember it's one of the sideways parabolas, and then the 9/4 is going to be my 4p for that situation. So I could actually graph this without really even plugging in very many points. Okay? However, I am still going to do a few points as well to go along with it. But first, let's look at the other way this could have gone. The other way I could have solved for this would be if I were to square root both sides here, I would see that t is equal to the square root of x minus 8 over 4. Now here's where the questionable part comes in. If you decide to do this, you have to choose whether you want to do the plus, the minus, or plus and minus, because I acted the square root there. Let's say I just choose the plus, right, like it is written right here, and then I substitute this in for t right here, right? So if I substitute this into t, then I'm going to get y minus 1 over 3 is equal to the square root of x minus 8 over 4. The one advantage here to this one is if you're trying to go for the original function notation type of stuff, okay? So in that case, I could easily multiply by 3 and add the 1, in which case I would get this. 3 square root of the x minus 8 over 4, and then the plus 1 would be out here, which is essentially the same as if I had plugged this into the t value here, basically, right? So either way, I end up with the same thing. And I chose the plus, okay? Now, this was, we already established this was a parabola. But if you remember some of your old school training, this right here, if I simplify it a little bit, becomes 3 over 2 square root of x minus 8 plus 1, which is just a square root function, right? The top half of a parabola only, and it's been shifted 8 to the right and 1 up, and it's been stretched vertically by a factor of 3/2. Okay, so this would have been the original function notation. Like I could have put f of x equals, and then this would be some function. But notice we've actually lost a little bit of information there by doing this, because over here I had the full parabola, whereas right here I've just got the top half. So it just depends on your goal. If your goal was to eliminate the parameter and have an old school function, then this is the way you should go. And to be clear, an old school function has just the plus or just the minus, okay? But if you want to keep the original information, you could always write this as plus or minus 3/2 square root x minus 8 plus 1. This one would be a function in the old school definition, and this one would not, okay? Now, if I keep the original information and substitute it this way, I can actually get the entire graph of the parabola. Okay, let's go ahead and draw that out. I know that my vertex is going to be at 8, 1, right? Same thing here, it's been shifted 8 to the right and 1 up. Okay, so I've got a graph that looks like this. 1, 2, 3, 4, 5, 6, 7, 8, and 1 is right here. So I've got 8, 1. And then we should probably plug in a few more values, right? Well, remember when we're doing a parabola, we always like to do the lattice rectum. Okay, so my p-value here for p is 9/4, which means that my p-value is 9/16, right? Okay, so then I'll actually have a very, very skinny lattice rectum. 4 times p being 9/4 would be on either side of where the focus is. I would have to actually add 9/16 in this direction here. And then I could go 9/2 in each direction, here and here. Not 9/2, 9/8 in each direction here and here. Okay, so then my parabola is going to look like this. It's going to be kind of skinny, with these points right here being half of the lattice rectum, right, which is 9/8 up from 1, which means this would have a y value of 9/8 plus the 1 here that's in the center, right? So that would be 17/8. These are already getting kind of yucky, aren't they? And then of course it would have to be a distance of p here, the 9/16 outward from 8. So 8 and 9/16, yummy. And then of course this point down here would have the same x coordinate, 8 and 9/16. And then it would be 9/8 down from 1, which would make it -1/8. Okay, so that's if we want to graph it old school, right? We could do that. But also don't forget that with the t values, I could make a little chart, and sometimes this is exactly what you want to do. A t chart, and then that'll give you x and y coordinates. So we just think of some t values, like t equals 0. When t is 0, up in the top, you'll notice I get 8 and 1. So 8 and 1. That's our vertex right here, right? So t equals 0 gives me that center point. And that should give you an idea of how the parabola is going to be formed. If I go in the negative direction, I'll get one side. And if I go in the positive direction, I'll get the other side. Okay? So here, let's say I plug in -1. When t is -1, I've got 4 times -1 squared, which is just still 4, plus 8 is 12. And then for the y value, I'll have 3 times -1 is -3, plus 1 is -2. Okay? So 12 -2 is going to be a lot further out. Like about here and here. And then what if I do +1? Plug in +1, I'm still going to get 12, but in that case, 3 plus 1, I'm going to get 4. So that's going to be in that same parallel x value here. See, they both have the x value of 12. So it's the squared that's going to give us that pattern. And you can continue to do more of these things. You know, let's say I plug in 5 here for what? -2 squared is 16 plus 8 is 24. And then -6 plus 1 is -5. And then 5 squared is 25 times 4 is 100, plus 8 is 108. And then 15 plus 1 is 16, right? So you can make the chart by just picking out t values. And a lot of times with these functions that we have, we'll get very nice values for x and y. So you have both ways of graphing these things here. Okay, next. Let's do something similar to this one. Let's see if I can get a graph, and we'll start by eliminating the parameter. Now remember, eliminating the parameter doesn't mean I'm leaving parametric equations behind. It means that for a moment I'm stepping out of parametric form back into rectangular form just to see if I will recognize the object that I get. And once I recognize that object, I can come back to the parametric equation, which is typically going to be more generic and more able to do things anyway. Okay, so here, for this one, I'm going to eliminate the parameter by getting some similar objects. I'm noticing that both of these have e to some power times t, right? So if I were to get something in terms of e to the t, I could easily plug it into the other one. This is what I mean. Right here, if I do x minus 9 is equal to e to the 3t. Right here, if I take the third root of both sides, third root of x minus 9, the third root would just divide this by 3. That would give me e to the t. Well, over here, I could do a rewrite like this. I could say that y is equal to e to the t to the -2 plus 1. Remember, power raised to another power just means they're multiplied, and that's exactly what I have. But lucky for me, e to the t is what I have solved over here. So I'm just basically going to plug this in for here. And that's going to give me y is equal to the third root of x minus 9 to the -2 power plus 1. So then there's a couple of ways I could simplify this, right? I could do y is equal to 1 over. Well, let's just do this. Let's do this plainly. X minus 9 to the -2/3 plus 1, right? That's one option, the -2/3 power. Or I could go straight for the actual thing, which would be 1 over the third root of x minus 9 squared plus 1. Either one of these is perfectly fine for your equation. Okay? Now, what kind of shape do we get from this? Well, let's take a look at a few things. First of all, obviously x can't be 9, right? If x were 9, I'm going to get some sort of asymptote. And also, from the parametric equation, there's no way for e to some power to be 0 by itself, which is not going to allow x to be 9, right? Since I'll never have 9 plus 0. Here's another thing. Since these are exponentials, they're never going to put out negatives by themselves either. So I'm always going to be adding a number to 9, which means the domain restriction of t here, imposed by t on x, is going to be only that I have everything greater than 9. Okay? You find that a lot with the exponential functions. You tend to only get one side of things because of the way they can only put out positive values from themselves. Okay, so for this one right here, I've got my equation. Let's just plug in a few values for t. T, x, and y. Let's see what happens when t is 0. When t is 0, I have e to the 0, which is 1, plus 9 is 10. And here, e to the 0 is 1, 1 plus 1 is 2. Alrighty. What happens when t is a negative number, like say, negative 2? When t is negative 2, I'm going to have e to the negative 6 plus 9. So that one I'm going to have to crunch. E to the negative 6 plus 9 is practically 9. It's practically 9. 9.002. We'll stop there. Okay, and then if I plug negative 2 into here, I get e to the 4. Wow, that's going to be huge. Plus 1. 55.6. So it's getting really close to the asymptote that we mentioned before, right? And therefore it's getting really, really, really tall. And then let's see what happens when I plug in just a good old 1, right? That's going to give me 9 plus e to the 3, which is 29.1. And e to the negative 2 plus 1. Which is 1.14. All right? So you can see these numbers are already blowing up in size, but they'll give me sort of an idea of what's going on here, right? From here you can tell x is always going to be bigger than 9, okay? From this statement right here, I can tell x is going to always be greater than 9. Also, this exponential here also cannot put out anything negative or 0, and it's going to be plus the 1. So y is going to always be greater than 1 here, okay? That should sort of make sense to you. Look at the way these things are shifted, and look at the asymptote that results, and then the horizontal asymptote that would result from the plus 1 being a shift upwards like that. Okay? So I can sort of get the idea of what the shape is that I'm drawing here. If I label this asymptote right here as x equals 9, and then I'll label this asymptote right here as y equals 1, then the shape that I'm drawing here is showing me something like this. And of course, this is just a rough, offhand sketch, but as long as you get the right idea going for this, okay? Now, in general, is this the graph of this function? No. There's actually a piece left off, There's the piece that's on this side over here. right? The piece that's over here could either be up here or down here, right? And the value of that is going to come from basically if you plug in something like x equals 0, right? Which can't happen for this parametric equation. But if you were interested in what the rest of this graph would look like, right? You could tell that if you plug in x equals 0, then what you're going to get is 81 third root of that, 1 over that, plus 1, which is just going to be a little bit bigger than 1, which would be over here. So technically the other part of that graph would be here, like this. Okay, but that's not part of our graph. We said we wanted this parametric equation as our function. So I was restricted due to the nature of what that parametric equation is. Okay? Oh, and also on the last one, we forgot to do one thing too. Let's do the flow, right? The flow of t from negative to positive, okay? Notice the flow of t would be this way. Because when it's negative, it gets closer to x equals 9. And when it's positive, it gets closer to x being something much, much larger. On the last graph, we forgot to do that as well. Let me just label the flow here. 0 is the middle point, and then as it gets more positive, you notice the y value is positive. So the flow is going to go in the upward direction right here, like this. That's the actual flow of our parametric equation. It would graph this way. It would want to do that way. Okay, next. Right here I've got x equals 2 cube root of t and y equals t plus 3. Let's eliminate the parameter in such a way that I can get a y equals. This one's pretty straightforward. I'm just going to get x right here in a position to solve for t. So when I do that, I'm just going to have to divide x by 2, right? Divide by 2. And then I'm going to do a third power. And that's going to be equal to t. So then I would plug that in here. Okay? So then my functional equation there, my basic functional equation, is going to be x cubed over 8 plus 3. Right? That's what it becomes after I eliminate the parameter t there. Which is just a cubic that's been slightly compressed vertically and moved up 3. Right? So if it's a cubic that's been compressed and moved vertically upward, right? So I'd have 1, 2, 3. But it's been severely compressed, so then I'd have something that was, kind of like something kind of like that. Okay, now have we been restricted? That's the shape of this function. Now let me go back and double check. Can t be both positive and negative here? Yes. Third root's okay. If it was a square root, you may have to worry. Okay, but since it's a cube root, it can handle positive and negative, and it outputs both positive and negative. And here, t is just linear, which can handle both. So this will actually be the shape of that graph right there. Where are we at if t equals 0? Well, if I plug in 0, x is 0, and if I plug in 0, y is 3. So I can actually say that that center point right there is t equals 0 right here. This point right here is t equals 0. Okay, so then what happens if t equals 1? Cube root of 1 is 1 times 2 is 2. And then 1 plus 3 is 4. Okay, so I've got some point over here that has the coordinates 1, 4. My scale's a little bit off. And that's going to be when t equals 1. And that's all I needed in order to label the flow of the graph here. Obviously, it must be flowing in this direction here. That is the direction of increasing t. Okay, one more. X equals the ln of 2t, and y equals negative 3t squared plus 1. So right here, I'm going to be going forward, straightforward, just like in the last few right here. I don't need to do any intermediate solving. I just need a straight, what does t equal? Okay? So from that top one right there, x equals the ln of 2t. If I just raise each side to the e, I have e to the x is equal to 2t. And therefore, 1/2 e to the x is equal to t. So I'm going to take this and I'm going to plug it in for t. Alrighty, so then what function is that going to give me? That's going to tell me that y is equal to negative 3 times 1/2 e to the x squared plus 1. And then, of course, if I square the 1/2, I get 1/4 times the negative 3. So that's negative 3/4. And then e to the x squared is just e to the 2x. And then it's plus 1. Okay, well, that's just your typical exponential function that's been shifted and stretched a little bit, right? So this is the shape that I'm going to be obeying right here. And let's take a look at our original equations. In this original equation right here, t must be greater than 0, right? Because ln of 0 is undefined, goes towards negative infinity, and ln of a negative number is complex. So I'm going to stick to t being positive only, right? Well, that's already a restriction on this, and I'm obviously going to start with something slightly bigger than 0 when I'm doing the plug-in for the flow. Okay, so then x right here could be negative or positive, though, because remember, ln of something, if I pick t small enough, like if I pick t to be 0.1, ln of 2 times 0.1 is going to be ln of 0.2, which is going to be a negative number. Or if I pick t big enough, like 10, ln of 20 is a positive number. So x can be negative or positive here. That's not a problem. And then, of course, y right here can be both, but looks like it's going to be capped at 1 here, right? Because this squared right here, this is always going to give out a positive times a negative. So it's always going to be 1 minus this, which is telling me that y is going to be less than or equal to 1 at all times here. So, you know, a few of those things to notice whenever you're looking at these things that can help you when you're drawing your graph here. But just from what I know of exponential functions, right? The negative out here makes it reflected vertically. And the e to the 2x normally has a shape that does this. Okay, but then we're going to flip it vertically. But then also we're moving it up by 1. So I've got a horizontal asymptote at y equals 1, which should make sense, right, to this statement right here. Okay, and then I'm going to have something that on the negative side makes it very, very small, and then on the other side, very, very large, right? So let's see, when y is 0, we have the square root of 1/3. So it's going to look something like that. And it's gonna use that entire graph. Let's double check with some values of t, right? Let's get some values of t to double check this. Okay, so t, x, and y. When t is 0, right? T is 0. Oh, why did I pick that? I already said t can't be 0. I'm losing my mind. T can't be 0. When t is 1, right? Then I'm going to have the ln of 2 for x. The ln of 2 is 0.69. So 0.7, let's say. And y is going to be negative 3 plus 1, which is negative 2. Okay. T can't be much less than that. Let's try what happens when it's 1/2. That would give me ln of 1 for x, which is 0. Okay, so that's actually going to be this point right here for us. Right, this is t equals 1/2 right here. T equals 1/2 right there. Whereas t equals 1 was somewhere over here. T equals 1 is right there. Okay, by the way, when t is 1/2, I have negative 3/4 plus 1. Right, yeah, because when x is 0, yeah, which is 1/4. Okay, well, that's enough information to get the flow of the graph there. So which direction is this one going? Right, obviously it's going this way. Right, like this. Do they always go from left to right? No, they don't. And, you know, in the last scene you saw an example of when that happens. Okay? They don't always have to go that particular way. The real difference here is the x controlling it, right? When the x is going to be negative and when it's going to be positive as for the flow there. Okay? Now go take a look at what these look like really in GeoGebra. It can graph these things and show you the little intricacies much better than I can. Okay, so let's take a look at these 4 examples. I'm going to take the approach here like a fresh start because I want you to see how I'm putting these into GeoGebra, because the technology side to this really does give another dimension to your ability to understand these things. So I really recommend, after you've watched this, to go and try your own parametric equations in GeoGebra. Also try them in Wolfram Alpha or any other software, Mathematica, Maple, whatever that you might be comfortable with. GeoGebra is very good for people just starting out. The commands are easy, and it's easy to look things up if you need help with it. Okay, so in order to do parametric equations, really all you have to type is just one command, but I like to be able to show you the flow, so I'm going to do 2 things. I'm going to start by creating a slider, which I'm just going to call P. So P, I'm typing at the bottom, P equals slider, and I'm just going to say the minimum value is going to be a -10, maximum value +10, because typically, you know, those are big enough numbers that it'll go off the screen anyway, and I'm not doing anything rotational, so I don't need a 0 to 2 pi, so -10 to 10 will be fine. Increment, I usually do a 100th, just so that it has a nice flow to it. If you want something a little bit smoother, you can also do a 1,000th like that. I'll show you what I mean. Speed, typically, I'll just do a 0.3 so it's not too fast. And you don't really need to worry about any of the other things. You're going to do a slider like this. Okay. And then I turn it off because you can get to the slider here. And all that's going to do is that's going to serve as a way for us to control the flow of our graph, or a point on the graph. Either way you want to look at it, the point on the graph or the flow of the graph itself. So to create a parametric set of equations here to draw a curve, what I do is I literally type curve. And that's the command you want at the top. It has two expressions, the parameter and then the parameter endpoints. So the first one we were interested in was 4t squared plus 8. So I have 4t squared plus 8. Then for my next expression, it was 3t plus 1. My parameter was t, and the start value on that one, we're just going to say -10, end value 10. And you'll notice it drew the graph over there. Okay? So before I even hit enter to put the command up there, you can see the shape that it's supposed to be. Now instead of just doing the numbers here, what I'm going to do is I'm going to draw this in a flowing pattern. So instead of the max value being 10, I erase that and I put P, the value of the slider that is up there, and I hit enter. So now notice on the slider here, if I change the value, it actually draws the shape for me. Right? So here's what's going to happen. I'm gonna bring this grid over here so that you can see, and then I'm going to hit play on this so that you can see, like, as the value increases of my t value, this thing is going to draw. And this is actually what we've been calling the flow of the graph. Another way of thinking of it is the direction that I would be drawing the graph in. Okay, so as you can see, the actual flow of this one is in that upward and to the right eventually. Right, comes up and left and then turns to up and right. And it's the sideways parabola as we stated before. It has the vertex at 8, 1 and all of the other values that ensued from there. Okay, so for the next one, the next curve, we had a curve. It was 9 plus e to the 3t, so I'm going to use parentheses for 3t. And then my other expression was e to the negative 2t plus 1. Of course, my parameter is t. And I'm going to pick -10 again, and then the upper value, again, I'm going to pick p, so that we can do the controlled drawing of this again. Okay. Now, as t is negative, right, you're going to see it go. See the way it draws it? Coming from that upward portion of infinity there. As t gets more and more negative, the point is like way up there. And then the flow is to come down the curve in this direction, the way it's going to be drawn there. Okay? Now notice, if I were to punch in the equation, y equals parentheses x minus 9 raised to the power of -2/3 and plus 1. It fits that perfectly, right? Except it's both sides. Remember we were talking about that. Because this thing is based on exponentials, our graph is actually just one side. See, when I turn ours off, this is the full graph that you would have done in standard form, right? But our parametric equation is only the right half of that because of the way we've used exponential functions to design these. Okay, next curve was 2 times the third root. Now, instead of the third root, what I'm going to do is t to the 1/3 power. Essentially the same thing for our purposes here. And then the other one was just t plus 3. Our parameter is t, and I'll go from -10 up to p again. Okay, and here's our function right here. See the way it's being drawn? We'll give you the flow there, right? This is the actual flow of our curve, and this one, as you can tell, is a lot slower. and it's based off of t to the 1/3. Right here, when it gets to that middle point, it might seem to speed up a little bit, just because it's coming to that focus point. You see it darted through right there real quick. It's sped up and now it's slowing back down again. Okay. And again, if I were to type in y equals 1/8 times x to the 3rd plus 3, right? You can see that our graph is the same as that graph. The last example, I have a curve that was the ln of 2t and -3t squared plus 1. My parameter was t, and I'll go from -10 up to our slider value there. Okay. And we do have the exponential function here. It's taking a long time to get there. It's almost there. There it is. And you can see it's just like what we were talking about there. The graphics are having a little bit of a glitch for us there. Let me go ahead and just max it out. And we have the exponential where the upper horizontal asymptote there is at 1, and it goes through the upper part of the y-axis just to strut into a little bit of the x and then skyrocket downwards like an exponential should. Next, I want to show you 4 more examples that are still the same kind of thing, but they're in a different field, if you will, because they use a lot of the trigonometric interactions that we use. And you might think that that would bring about something trigonometric when actually a lot of times it doesn't. And using trigonometry in this way often helps us describe things that are much more difficult any other way. You saw a small example of this in the first scene when I showed you that ellipse. And these are very similar to that. Okay, so let's start with the first one over here. X is equal to 2 times tangent theta, and y is equal to 5 times secant theta plus 1. And theta is said to be from 0 to 2 pi. You'll find that very often that's going to be the case with these sort of things. Okay, that you'll have a lot of 0 to 2 pi type of stuff. Every once in a while, though, you may have something slightly different, and you have to just look at what you're working with and whether or not you're willing to include asymptotes and things like that. Okay, so the first thing you want to do with these, just like with that ellipse in the first scene, is you'll want to go ahead and eliminate the parameter. But after you do a couple of these, you really should just sort of recognize which shape these are going to give. And the shape comes directly from whichever trigonometric identity connects the two things that you're using there. So I need a connection between secant and tangent. A connection between secant and tangent comes immediately from a Pythagorean identity. I know that secant squared of theta minus tangent squared of theta is equal to 1. So I'm going to get some squares, there's going to be a subtraction, and it's going to be equal to 1. Okay? Now, if you don't already suspect, let me go ahead and burst the bubble. It's leading towards a hyperbola because you have squared things, they're subtracted, and it's equal to 1. So right here, secant squared is going to be from this equation right here. Notice if I subtract 1 and divide by 5, I will get secant theta. So that means that y minus 1 over 5 squared minus, now tangent comes from up here, if I just divide by 2. So it'll be x over 2 squared. And it's going to equal to 1 because this is secant, then squared, then tangent theta, then squared, right? Subtracted. And that's our trigonometric interaction. We'll simplify this a little bit. I'm going to have y minus 1 squared over 25 minus x squared over 4 is equal to 1. Okay, so notice this is the hyperbola that's centered at 0, 1. The negative is on the x, which means it's going to be a vertical hyperbola. Okay? And tangent and secant are both capable of positive and negative values, and they have asymptotes at the same locations because tangent and secant are dividing by 0 whenever cosine is 0. Both of them have the same asymptotes for theta. Okay, that should make sense to you. Whenever we're graphing the hyperbola, right, there are those asymptotes that they fall into. So those asymptotes are going to be what occur when I start to approach those particular values of theta. Okay, so let's get a rough sketch of what this guy is going to look like. Right here, I'll just draw it in like this. My center is at 0, 1, so that's here. And then it's an up and down hyperbola. And the b value is 5. So I'll go 1, 2, 3, 4, 5 up. And that's going to be one of my vertices. And then I'll go 1, whoops. Yeah, let me redo that. Let me make that a little bit better spaced. 1, 2, 3, 4, 5, 6. There's one of my vertices. My center is here, and then 1, 2, 3, 4, 5. There's my other vertex for the bottom piece. And then my A is only 2. So 1, 2, and 1, 2 means that I have the little box, right? Remember the box? That I could draw my asymptotes with. Okay, so my asymptotes are going to be, let me get my straight edge here. Hit both of those corners. I'll just go ahead and make them solid red for now. All right, now let's get the other one going here. Asymptotes. Almost done. Okay. So then my hyperbola, being the one in the y direction, of course, is going to hug these asymptotes up here. It's going to hit this vertex here. It's going to come back out and hug the asymptote there. Same thing, right? Down here it's going to hug. It's going to bounce at the vertex, and it's going to go back out this way. Okay? Now we have two separate pieces here. But remember, tangent and secant are both capable of positive and negative numbers. So if I chart this out just a little bit and just get an idea of what's going on here, right? Let's do that so we can see what's happening. T, X, and Y. All right. So let's see. When T is 0, right, the beginning of my little interval here. Tangent of 0 is 0, and secant of 0 is 1, so 5 plus 1 is 6. Okay, so notice that is this vertex right here, 0, 6, right here. That's t equals 0. What about when t is, say, pi over 4? 45 degrees, right? Pi over 4 radians. Tangent of pi over 4 is 1, so I'll get 2 for x. And secant of pi over 4 is square root of 2 over 2. Okay, let's go ahead and crunch that one. 5 divided by cosine, that's basically how I'm going to get it, plus 1. 8.07. Okay, so practically 8, right? 8.1-ish. So at 2 and then 8, that's going to be like way up here, right? So you can see the flow now when it's pi over 4. What about when it's pi over 2? Well, at pi over 2, tangent is undefined. So is secant, right? Both of these are going to be division by 0 when I hit pi over 2. Guess what that means? This asymptote right here, the flow is this way now. Remember, we were doing this. We started here, went to here. This is t equals 0. This is t equals 1. The flow is this way. So that means just this portion of this asymptote right here is t equals pi over 2. That portion of that asymptote right there, when it actually gets to infinity. Think about that for a second. I actually have a t value in my little list of values here. It's in this, in right here, right? I guess I should technically include this, that this can't equal pi over 2, but it's in there. It's in that interval. And it physically represents that asymptote. So guess where it comes up after that? What if I do something just a little bit bigger than pi over 2? Like instead of 90 degrees, let's go a little bit further, like 120, right? So that'd be 2 pi over 3. Tangent of 2 pi over 3 is negative, and so is secant, right? Tangent of 2 pi over 3 is like negative square root of 3. So 2 tangent, 120 degrees, negative 3.4. Oh, 3.5, really. Okay? Then what about the other one? That would be 5 divided by cosine 120, and then plus 1, negative 9. Well, look at where that is. X and Y are both negative, right? Negative 3.5, negative 9, that would be somewhere right here, about right here. This point right here is t is equal to 2 pi over 3. What happened? It started here and it was flowing this way, and then all of a sudden, whoop, it went around to this side. I have this idea for people that are just learning this stuff. It's something I call thinking projectively. Imagine the surface here is the surface of a globe, a sphere. This line right here, from the perspective of a round thing, a line could really be something that's going around like a circle. So imagine if you were in a spaceship looking at Earth and someone were traveling. It would be like they would disappear around one side and then they could fly back around the opposite end. That's exactly what you should picture here. This hyperbola right here is flowing this way, and then it wraps around the other side, right? The undefined side. And then it comes up on the opposite end. And guess what? Which way is it flowing? It's going this way, like this. And then it's going to hit this vertex. What happens when I plug in pi, right? When I have pi, tangent again is 0, and secant is negative 1. So negative 5 plus 1 is negative 4. That's this vertex right here. So it keeps flowing this way. And then what else happens? It's going to wrap around again. It's going to go around this way, and it's going to come up here, right? This asymptote right here is going to be represented when t is equal to 3 pi over 2. The other place that these are undefined. Undefined. So anything larger than 270 degrees, right, between 3 pi over 2 and 2 pi, is going to be on this side right here. It's going to wrap around, and then it's going to flow this way. And then meet back up there again. Just like you would expect something from trigonometry to do. But a hyperbola isn't necessarily a trigonometric object, is it? It is now. The pattern of these things gives this particular shape to you. And it's not actually a constant speed the whole time either. It's actually going slow for a little while. And then notice it goes like it takes off. And all of a sudden, as soon as it hits pi over 2, it's disappeared on that asymptote there. Okay? So a very interesting interaction there. You can turn trig into a conic section. Okay, same idea, and you may not have much exposure to these, but I want to talk about it anyway for generic audience here. The hyperbolic sine and cosine functions are named thusly because of this same kind of interaction, the same kind of connection. Okay? The hyperbolic sine and cosine, just real quick, in case you've never seen these before, are defined using exponentials. Cosh, or hyperbolic cosine, of t is equal to e to the t plus e to the negative t divided by 2. And sinh, hyperbolic sine, of t is equal to e to the t minus e to the negative t over 2. Okay, so basically I'm just using e to the t to define these two things, right? However, they do have a life of their own. They do have their own uses of their own. They have their own place in physics, chemistry, other sciences like that, dealing with anything from electric interactions all the way to tension on lines and strings and things like that. Okay, so the connection here is this. If you square hyperbolic cosine, cosh squared of t, and you square sinh, hyperbolic sine squared of t, and you subtract them like this, you get 1. So it sounds a lot like trigonometry, right? Except instead of plus, it's a minus. I hope you can already see where this is going. It's the same kind of interaction that we had right here. This cosh is equal to x, sinh is equal to y. This right here is going to tell me that for my particular equation here, x squared minus y squared is equal to 1. And therefore the graph of this is also a hyperbola. However, different than before, hyperbolic sine and cosine don't have the same restrictions. Cosh and sinh do not have asymptotes. However, they do have limits, pun intended, right? Cosh only gives out positive values, okay? So right here I can tell you, because of the way cosh is, I'm just adding 2 positives here, you see, and then dividing by 2. Sinh can give out positive and negative values, but cosh cannot. So that's telling me that x is always going to be positive here. In fact, cosh has a lower boundary, right, of 1, to be honest with you. In this case, that's going to restrict my x value here. Okay? So even though this is a hyperbolic curve, I'm actually only going to get one of the 2 curves, right? Normally hyperbolas are 2 pieces, and because of the way cosh is set up, I'm only going to get one of them. Okay? So you can see that these are both over 1, and my center is 0, 0. So I'm getting something that looks like this. My center is here at 0, 0, and then my length is 1. So at 1, I should expect a vertex, right? Here's my center. I should expect a vertex there. For the terms of the hyperbola, remember, I need to go and draw the little box, right, that will give me my two asymptotes. Okay, but those are both going to have slope of 1 and -1. So as you can see, I just have this and this. And my shape is going to do this. Okay? And then this is the only side I'm going to get. Let's test that out. Let's plug in a few values. Right? Let's do a little t chart here. T value, x value, y value. All right, so when t is 0, x is the cosh function, y is the sinh function. Here's some good news for you. You could plug these in the long way, right? Do e to the 0 plus e to the -0, blah, 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 blah. Okay? I'm going to save you some time. On your calculator here, right, the same one, you might have noticed above the pi button where it says hype, H-Y-P. That stands for hyperbolic function. So if I hit second and that pi button, notice it has hype. It's like it's waiting. Right after that, if you hit sine or cosine, notice it doesn't say COS, it says COSH, cosh. So then I could just hit a number value, cosh of 0, and it will compute it for you. Cosh of 0 is 1. Okay? Sinh of 0 is 0. Okay? So notice this is my vertex right here. This is the t equals 0 spot, as should make sense, right? So if I go negative in the negative direction and in the positive direction, you'll see different points located on here. Okay? So cosh of -1 is 1.5. Cosh of -2 is 3.8-ish. Okay? Now if I do the positives, cosh is an even function, so you're actually going to get matching values here, okay, for either side, which is why, you know, cosh doesn't give out any negatives, you can tell. Okay, now sinh. Sinh of 1 is 1.2. Sinh of -1 is -1.2. I hope you're realizing sinh is an odd function. -3.6. And just to double check, 3.6. Sinh is an odd function there. So you're getting the same values but negative for that one. So you can tell right away why it's flowing the way that it does, right? When t is negative, I'm getting negative y values. And when t is positive, I'm getting positive y values. Okay? So 1.5, 1.2, t equals -1 is here. And t equals +1 is here. So you can see which way this thing is flowing, right? It's flowing this way, right? This way, which means it's also going this way. And as t gets bigger on either side, the x value is going to continue to go to infinity, and the y value will either go to positive or negative infinity, hence the pieces here, and why you're only going to get 1/2 of the hyperbola there. My x value never switches to a negative, right? There's no cosh value that will do that. So I'm only getting 1/2 of it here. So even though both of these things give me hyperbolas, right, it's completely different patterns and approaches, right? Here it's plain trig, which has both positives and negatives and includes its own asymptotes. Whereas over here, I'm getting something that's based off of exponentials, which is only going to give out those positive type of values. And sinh only becomes negative anytime this subtraction is the one that deals it out, not because of the exponentials. Okay, let's continue. We've seen one of the interactions between sine and cosine in the original scene, and it gave us an ellipse. Since these two 2's are the same size, right? The coefficients are the same size. What you should expect is that instead of an ellipse, it's actually going to become circular. The difference here is the 4 theta. Okay? The 4 theta is only different because it goes through the angles faster. I've changed the frequency on both of the sine and the cosine, which is just going to make it spin around the circle faster than it did. But you're hardly going to notice that, and it's still circular because these two arguments are the same, right? So in other words, what I'm getting here is if I were to do negative 2 sine 4 theta squared plus 2 cosine 4 theta quantity squared, notice that that would give me 4 sine squared 4 theta plus 4 cosine squared 4 theta. And if you factor out the 4, that tells me sine squared 4 theta plus cosine squared 4 theta. And again, since they're the same angle, this is going to be equal to 1, which is 4 times 1. So in other words, x squared plus y squared gives me 4 times 1. My equation is x squared plus y squared is equal to 4, which is a circle of radius 2, right? No coincidence. The radius is the number right here multiplied by the sine and the cosine. Okay, Mr. Simon, how is this any different than that one in the beginning then? It's just another round shape. It's another conic section? Sure. But did you notice that I changed up one of them to be negative? And I also switched the normal operating procedure of giving x the cosine all the time. So what's going to happen to the flow and the direction and the way this thing runs because of those couple of switch ups, right? Because I put a negative on one of them, x is going to be doing something opposite. And also I switched the sine and cosine. X is going to be based off of something different than what you normally expect. Okay, so I have the circle centered at 0, 0 with a radius of 2. The graph is exactly what you expect. It's a centered, a origin-centered circle, radius 2. So 2, right? 2, 2, 2. Give or take a little bit, right? Might be off here and there. Okay. Let's make a little chart now. Let's do a t, x, and y value chart. T, x, y. Alrighty. I only really need a couple of them, right? What happens when t is 0? Which, by the way, on this one, really, not t, I should be doing theta. Did I make that mistake over here too? I sure did. Look at that. I hope somebody caught me. That should be theta. Theta, x, and y. When theta is 0, I have sine of 0, which is 0, and cosine of 0, which is 1 times 2, right? 2. So notice 0, 2, that's right here. That's where t equals 0 right there. Normally we start our rotations here, don't we? Okay? So that's different because of the switch between the sine and the cosine. Okay? Now what about the flow? Well, let's see. When theta is pi over 2, that's actually not what we want. Let's do pi over 4. pi over 4 times 4 gives me pi, right? So sine of pi, also 0, and cosine of pi, -1, so I get -2. So notice I get this point down here. That's t equals pi over 4. It's already rotated from the top to the bottom, one way or the other. I don't know which way yet, because we need one more point. But notice it's already done half of the circle in only a quarter of pi. Okay? That's what I was getting at a minute ago right here. I did it again. I did t. I got t on the brain here. Theta and theta. Notice my theta right here, I'm gonna say it's restricted between 0 and pi over 2. Because at pi over 2, 4 times pi over 2 is 2 pi. It's actually gone all the way around. Okay? That's what the 4 has changed. It's making me go around in less amount of theta. So technically faster. Okay? So let's see if I can find another theta value here that will help me locate which way this thing is flowing now. Let's go a little bit further. And instead of pi over 4, let's do something in between those two, like pi over 6, right? Pi over 6, 30 degrees. Let's do that. Sine of 4 times pi over 6. Well, 4 times pi over 6 is 2 pi over 3, which is 120 degrees, right? So sine of that is going to be positive. Sine of 120 is square root of 3 over 2 times -2. So I'm getting negative square root of 3. Okay? Let's recap on that for a second, and I'll plug it in and show you. Okay, I'm plugging pi over 6, but times 4. So -2, let me put it in radians. -2 sine of 4 times pi over 6. And notice I'm getting negative 1.73, right? Negative square root of 3. So negative 1.7. Okay. Now again, cosine of the 120 is going to be negative, and cosine of that is 1/2 times the 2. So I'm getting -1 for this one. Okay. Also, don't forget to double check yourself. Notice I am actually getting -1, right? So what does that mean? Well, theta equals pi over 6 is going to be at -1.7, -1. -1.7, -1 is like right here. That's going to be theta is equal to pi over 6. Okay, so we figured out the flow. That's this direction. It's our typical direction, right? I'm flowing around in a normal counterclockwise direction, this way. Okay, so the negative, don't say that it didn't have an effect. Switching the sine and cosine may have given it the effect of flowing in the other direction, and then putting the negative on the x switched it back. Okay? So, still a circle, but changing the frequency just changes the amount of theta that I need. And, you know, switching the sine and cosine and the negatives can change the effect of the flow. Okay. Last one on the board here is one that you probably haven't seen. Okay? I'll just go ahead and spoil it for you. It's something that we call the Witch of Agnesi. All right, this is a special curve that has many different progressions of its shape. This is the basic one. Okay, this is what we call a equals 1. So what I'm going to do is I'm going to eliminate the parameter, and then on the rectangular side, it's actually a quite simple graph to draw out. Okay, so let's go ahead and do that. I'm going to eliminate the parameter by doing this. I'm going to square both sides here, x squared, is equal to 4 cotangent squared theta. And then I need a connection to sine. Well, cotangent squared, don't forget, is equal to cosecant squared minus 1, like so. Okay, so from here, notice that if I were to divide by 4, I'd have x squared over 4, and then add 1, I would have cosecant squared theta is equal to that. Okay? Well, I want to have sine squared, which is the reciprocal of this. To do a reciprocal, I really want this to be all one fraction. So I'm going to do a common denominator here, 4 over 4. So what I get is x squared plus 4 over 4 is equal to cosecant squared. Okay? So what does this mean? This means that sine squared, which is the reciprocal, is going to be equal to 4 over x squared plus 4. And then y is just 2 times sine squared. So if I multiply both sides by 2 times 2 times 2, then I've got my equation. Y is equal to 8 over x squared plus 4. Okay? So just your typical rational function has a horizontal asymptote but no vertical asymptotes. The horizontal asymptote being the axis itself. Let me just give you an idea here. So it would look something like this. And the cool thing about this particular shape is that what it also does is it caps like a blanket over a circle that fits exactly between the axis and itself, where the distance from this center point right here is a. So then the height right here is 2 times a. Okay? And the cool thing about that is for the parametric side, if you want to change to a different size circle and still have the Witch of Agnesi shape on top of it, you just do times a right here on each of these 2's. And it could actually increase the size of the circle that it blankets over, and also keeps it preserves the shape of this thing. And this particular thing is used in all sorts of applications, like waves and things like that. Okay? So trigonometric examples don't always give trigonometry. In fact, as you can see, very little of them actually give trigonometric shapes. But they do have a unique connection to a lot of important shapes that we do study. Okay, so let's do a quick run through of these 4 functions that we just saw. I've already got this one typed in, 4 times tangent and 5 secant plus 1, but instead of secant I put 5 divided by cosine. Same thing, right? Alright, so then the curve graphs to this, as you can see, the hyperbola as promised, centered at the point right here. Right, centered at 0, 1. And then I have my vertices at the 6 and -4 marks. If I were to set my counter to 0 here, notice my beginning point right up here, as it was supposed to be. And as I hit play, you can see the point take off. Went a little too fast there. So as it starts going that way, what you're going to see is that right around pi over 2, boom, it just disappeared. Remember, pi over 2 is 1.57, so we're almost there. Right here. It has gone into the undefined region, and then as soon as I let it go any further, it's going to appear on this other side over here. You see? There it is. And then it's going to peak out right as we're hitting pi. And then it's going to take off down the other side. And then at 3 pi over 2, it then appears at the other side, and then bottoms out here right at 2 pi. right? 6.28. It would have gone a little bit further, but you get the idea. Okay, so the next function that we were looking at was also a hyperbola, right? But I did it with the hyperbolic functions. So we have cos and sinh. Okay. So then I will let my A value get a little bit larger there. Okay. So as you can see, it's definitely that side of the hyperbola that we were discussing. And if I allow the point to exist on here, you can see there it is at the 0 mark, right? And the direction of flow is as we were talking about over here. If you ever wanted the other side of this hyperbola but with the same methods, I would have to put the negative on my cos function here, on my hyperbolic cosine. If I did that, notice it gives me the other side. You'd have to just find a way to figure out your negatives there. Okay, the next one was -2 sine 4 theta. So I'll do 4x here. Notice that gives you something really crazy looking. I haven't finished typing in the y values yet. 2 cosine 4x. And there we have it. We have a circle. And I'm going to put my point at 0. And notice when my point is at 0 there, right, it's at that top point as we were talking about. And as I hit play, you'll notice the direction of the flow is the counterclockwise version that we were talking about before. And it already cycled. You saw that it already got back up to the top. And I was only at a pi over 2, 1.57. See? It hit the top again. So this thing is going to have 4 cycles within a normal 1. So from 0 to 2 pi-ish, normally it would just have 1 cycle. Since we did 4 theta, 4x on this one, it's actually going to go around 4 full times in the normal 2 pi stretch. You see it's almost there now, and it's almost completing the 4th lap there. Alright. The last example on this one was the Witch of Agnesi that we did, where it was 2. I'm going to put divided by the tangent of x and 2 sine squared. Oops. Okay, and as you can see, we have the curve as promised. And the other thing you need to note is that we would also have the circle of radius 1, but that's been shifted with a center there to fit underneath. So that would be x squared plus y minus 1 squared is equal to 1. So as you can see, that circle fits right inside. And we do have other curves in this same category, like I was saying to you before, where the A is just whatever we multiply by each of the 2's in here, and that gives us a larger radius of the circle. But our curve is just simply this one, and here's the flow of it here. Right? This is the actual flow that we were giving it in that particular thing. Notice it is a backwards flow. I know I forgot to mention it in the actual scene. Okay, the flow is going backwards like that because of the way our x values are oriented here. Right? tangent being one of those types of functions that normally increases. Since it's cotangent, it's the reciprocal of it, naturally it's going to be a decreasing function. Cotangent is a decreasing function. Therefore, the x is going to go in an opposite direction than what you would normally expect. And there it goes. What about the reverse? What if I wanted to take a rectangular or normal, thinking that we've been doing for years and years here and convert it into parametric form? Well, most of the time that's actually pretty easy, considering that there's an infinite number of choices that we can use to make that conversion. Unless you have something very specific about the connection that needs to be there, you really have a plethora and variety of things that you could do to create a parametric equation. So for example, something like this. Typically the things that we have in our normal rectangular thinking have y equals, and this one's no exception. I could get it into that. In fact, that's what I'm going to do now. I'm going to get everything to one side except for the y, and I'm going to divide it out. So let's see, y is going to be equal to well, let's do 3y. Negative x to the fifth plus 9x. And then the 3 and the 4 is going to give me 1, right? Okay. So right here I'm going to divide by the 3, and I'm going to get y is equal to negative 1/3 x to the fifth plus 3x plus 1/3. Now, I have a direct connection between x and y. My first choice would be the trivial one, right? What if I just let x be t? Then y would be negative 1/3 t to the fifth plus 3 times t plus 1/3. Okay, now that's the trivial way to do it, and it's also a very uninteresting way. It's not going to change the speed, it's not going to change the orientation, it's really not going to do anything for you other than just say, hey, it's a parametric equation, right? And there are other choices. You can stick with linear, or you can, make it a little bit more lavish. Like, for example, if I let x be t squared plus 2, then y would simply be equal to negative 1/3 t squared plus 2 to the fifth plus 3 times t squared plus 2 plus 1/3. Notice all I had to do was, everywhere there was an x, I just put what x was equal to. And it really is that straightforward for this type of function, right? If y is already solved for, or vice versa, if x was solved for, you could do the same thing in reverse for y. You could do something like x is equal to e to the t, in which case y would be equal to negative 1/3 e to the 5t plus 3 e to the t plus 1/3. Any one of these three would be an acceptable parametric equation. And again, it just depends on what values you want to have, right? The e to the t here is never going to let x be negative, so you'd only get one portion. The t squared plus 2, x is never going to be less than 2, right? Here, x is straightforward every value of t. So it just changes with whatever your needs are. In general, if you just asked, hey, create a parametric equation, you could almost choose anything. Now, on the flip side, what if it's something specific, like some of those conic sections, right? Circle, for example, and you already know a nice pattern for it. Well, then you should definitely consult that pattern. For example, a circle, all I would need to know is the center and the radius, and I could convert this into a parametric equation that involves cosine and sine. So that's what I need. I need to take a look at what I'm dealing with here, right? The point 1, 2 is going to be somewhere right here, and 7, negative 8 is going to be somewhere over here. So of course I'm going to be interested in wherever the center is, right? And then of course the circle itself, as lopsided as I can. This is not too good. That's a little bit better. I'm working on it, guys. I'm working on it. Okay, so then I just need to know where that center is, and I just need to know my radius, right? Okay, well the center is going to be the midpoint of these two since they're both endpoints of a diameter. Okay, so if I can find the midpoint of these two, right, that's just the midpoint, which we have a formula for, right? And then also, since this is the center, then the distance from the center to one of those points is that radius. So that's all I need to do. The midpoint, or in other words, my center, is going to be equal to 1 plus 7 over 2, comma, 2 plus negative 8 over 2, which is going to be 8 over 2, which is 4, and negative 6 over 2, which is negative 3. And then once I have that center, my radius is just going to be the distance formula between the 2 points. So let's say I pick the 1, 2, right? So that's going to be 4 minus 1 squared plus negative 3 minus 2 squared. So I've got 3 squared, which is 9, and negative 5 squared, which is 25. 9 plus 25 is 34, right? So my radius is the square root of 34. Don't forget, those two formulas are from your basic algebra. If you're a little rusty on them, don't be ashamed, don't be shy. Go look at my college algebra on the Cartesian coordinate system and circles, right? We talk about the midpoint and the distance formula, right? Where you just add the 2 x's, divide by 2, add the 2 y's, divide by 2. And then the distance formula is difference of the x's, difference of the y's, both of them squared, added, square rooted. Okay, so once I know that though, I know that the standard equation of my circle is just going to be x minus 4 squared plus y plus 3 squared is equal to 34, right? Because it's the radius squared over there. And therefore my parametric form is going to be such that I just need to have the 1 over here. So I'm just going to divide, appropriately by the 34, or multiply, whichever way you want to look at it. X is going to be equal to the square root of 34 times cosine theta, and then plus 4. And y is going to be equal to square root of 34 sine theta, and minus 3. Do I have to put sine and cosine in those particular orders? No. I could actually flip-flop those. I could also make the sine and cosines negative, right? I could do the negative square root of 34 cosine as long as the plus 4 and the minus 3 are correct there, because that's the center. Okay? So a little bit of variety there, but if it's one of those structures you already know that we've talked about, then of course do one of those instead of just plugging things in like we were doing over here. Okay? So creation just comes from experiencing all of these other kinds of patterns that we use and then trying a few things out. Real quick, I just wanted to talk about that circle that we threw up there. So let's do that one real quick. I'm going to click a few points here. We were supposed to have the point 1, 2, which is here. And we were also supposed to have the point, let me move it up a little bit, at 7, negative 8. So 7, negative 8 is right here. Okay, so now let's type up our parametric curve. We had a curve, and it was the square root of 34 times the cosine of theta, and it was plus 4. Next, we had the square root of 34 times the sine of theta, minus 3. Parameter was theta, or t in our case here, And of course, I would be doing my normal 0 to 2 pi. And lo and behold, you can already see that is definitely the circle that has those 2 points in question. The center point we said was 4, -3. So as you can see right here, 4, -3 is that center. And if I pick a point somewhere on this curve, right, and then do the segment, you can see the length of that segment is the 5.83, which would be the square root of the 34 in question that we were talking about. And no matter where I move that point, notice the length of that segment, 5.83 over here, does not change, even though the coordinates of the stuff does, right? And as you can see, it stops on that 1, 2 point, and it actually will stop on the 7, -8 point as well, which means they're both actually on there. Incidentally, 9 zeros on there, that's cool. And so is -1, 0. Let's sneak a quick application of parametric equations in here. I'm not the biggest fan of football. I'm not really much into it. I'm not against it, but it, like any other sport, is riddled with really awesome math and physics problems, and I'm always up for a good math or physics problem. So here I have an application that I wrote down using some data that I looked up on Google about a local quarterback. Since I live close to New Orleans, you can guess. And of course, the intricacies of this problem in no way, in any shape or form, promote or demote or say anything about his actual performance, because I have absolutely no idea. But it is a really cool problem, and I did use the initial numbers from what I looked up on Google, so you can reference that if you want. So a football is passed downfield from a height of 6.5 feet. Now let me qualify. The person that I picked is 6 foot tall, and I'm saying that he's passing like this. So his arm is at least 6 inches above his head, right? Give or take. So around 6.5 feet above the ground, the football is released. Okay? At an angle of 35 degrees, about less than halfway, right? Less than 45. With an initial speed of 76 feet per second, which is the Google listed speed of this person's average throw. Okay? So then from all of this information, figure out what height is the ball after 2 seconds while it's in the air, and what is the maximum height that the ball is going to reach for this particular throw. Okay, of course that's going to change slightly. It's going to have a perturbation, if you will, depending on each throw. And assuming the pass is incomplete, right? Maybe there was nobody down there to catch it. How far away does the ball strike the ground? Or hell, maybe it's a practice throw, right? Maybe we're just trying to see how far it can throw it. Whatever. Okay, let's say it strikes the ground. They want to know how far away from the person it does so. Okay, so don't forget what I've got is the person throwing the ball and it's striking the ground, right? That's what we know. And of course, if we're neglecting wind resistance and other types of frictions, as soon as the ball leaves his hand, of course you have to have friction to throw the ball, so after it leaves his hand, we're going to neglect everything else. We can assume that the path is fairly parabolic, okay? So we'll start with the idea that our y position, which is going to be the height, okay? Y is going to be the height, and x is going to be the distance outward, right? So my x is going to be how far the ball travels this way. My y is going to be how far the ball is off of the ground. Both of these are going to be measured in feet. Okay? Now naturally, the arc that it's being thrown in itself is going to be, like we said, fairly parabolic. So that means I can have y equals ax squared plus bx plus c. Some parabola, right? Now I want to turn this into a parametric equation because some of our initial information is not just about the height and the distance. In fact, not very much of the initial information is about that. It's kind of like what it would be in real life. Okay? These are all things that are more measurable than if you were to try and take several snapshots of the ball in the air or try to measure the ball while it's in the air. It's rather difficult to do that. Okay? So we're just making a few assumptions here, like the thing being parabolic for the most part. However, I need it to be parametric because both of these are going to be related to some sort of time-based information, like when I released it is time 0, right? And the fact that it's based off of some sort of speed, which is distance divided by time, okay? So in this case, what we're going to be doing is converting this into a parametric equation where the t value, the parameter of the equations, is a time variable, okay? So then we do this. We assume that with neglecting all of the other frictions and things like that, since there is nothing slowing the ball down, then the speed in the x direction, okay, the speed just in the x direction is going to be constant. All right? What does that mean? It means, therefore, my x variable is going to be equal to some sort of velocity times time. Okay? Now, this velocity, since it's constant, is the same as if it were the initial, in other words, v sub 0. Okay? So if I can figure out the initial velocity of the x direction, I'm just going to show you what it is real quick, then I can already have my parameterization of x. Okay? Now think about this. If the ball is being thrown at a certain angle, right here, right? I'll just translate that idea to here, like right here. And this will be that 35-degree angle, right? Well, notice that if I take this to be a size 1, in other words, 1 pass, right? Then the cosine is just x over 1. The cosine of the 35. Now, it's not just 1 this time. It's velocity, whatever the velocity is. So v. Okay, so x over v is cosine of 35 degrees, or in other words, x is going to be equal to v naught cosine of 35 degrees times t, right? Or if you want, just v times cosine of 35 degrees, okay? So for my parametric equation, I already know what I'm going to let x be. I'll write it generically here, and then I'll use the one over there. In general, I'll be able to do this. X is equal to some initial velocity, cosine of the angle, times t. Now substitute this into your y equals parabola equation here. Okay? So real quick, look at what happens when I do this. What I get is a times v naught, right? The cosine. In fact, I won't even put the cosine right here. I'm just going to symbolize it v naught x. V naught x like this. Times t squared plus b times v naught xt plus c. Right? If I'm just plugging in the initial velocity times time for x, I'm plugging it in here and here. Notice that what I'm getting right here for this is something that's still a distance divided by a time times t. Okay, not the t, just this part right here is just some sort of velocity, distance over time. But it's in the y direction. So whatever this b is times the v naught, it must be giving me the y initial velocity. And on top of that right here, this coefficient, the a times the initial velocity of x, but that quantity is squared, and then I have t squared This piece right here is in the units of some sort of quantity over the seconds squared, right? So time per unit squared, or time per second squared. Amount of distance changing per second squared. That's acceleration, in other words. Now later on in the course, when we start talking about actual vector quantities and things like this, I'll go into much more depth of what's going on here. I'm just sort of giving you a hand-waving argument here of what I'm about to write down. Okay? Here's the justification of this. What I then get is y is equal to -1/2 gt squared plus v naught sine theta t plus h naught. Okay? So this is a parametric form, one possible parametric form of a parabola. This particular parametric form is what the position of some sort of projectile, ball, object, okay, in the grips of gravity, flying through the air while you're given some sort of initial speed where there's nothing to slow down the x direction, okay? Obviously, gravity is what's making the ball come back down, right? Which is why this is more complicated than this, okay? But the initial velocity, the angle that it's thrown at, gravity of the field that it's in, and the initial height. So let's see, what does that make for us? In our situation, that means that our path, P, is equal to the parametric equation, where x is equal to 76 cosine 35 degrees times t, and y is equal to -16 t squared plus 76 sine 35 degrees times t plus 6.5. Now, hang on a second there, Professor Simon. Where did that -16 come from? Well, in case you haven't seen this before, and it's possible, it's fine. The g right here for gravity typically has two possible values. It either has 9.8 meters per second squared, or it has 32 feet per second squared. Okay? So depending on your situation, right, all of our stuff is measured in feet. So of course I'm going to pick this one, right? And -1/2 times 32 is the -16 aforementioned in the equation there. Okay, so now let's continue to answer these questions. Okay, letter A, what height is the ball after 2 seconds? Okay, so when t equals 2, right? Lovely thing. T is the measurement of time in seconds, right? That's how we set it up, because my initial speed is based on seconds, feet per second. So that means my t naturally here is in seconds. So what I need to do is the height. Remember, the height is just the y value. So I'm simply going to do this calculation of y and plug in 2 for t. And what I get is that y is approximately, let's see, -16 times 2 squared, 76 times 2 times sine 35, plus 6.5. I get 29.68. So 29.7 feet in the air, right? Off of the ground. Next, what is the maximum height that the ball reaches? Okay, well, remember, this is a parabola that we're dealing with here, right? And in a parabola, there is a vertex. And that vertex, in normal algebra, we calculate for any parabola the h value was negative b over 2a, and then you plug that in. Or if you want, you can take the derivative, set it equal to 0, right? Do the maximization piece right here. Okay, so max height. The time that it takes to do that is going to be negative b, which is 76 sine 35, degrees, divided by 2 times a, which is 2 times negative 16. Okay, notice the negatives are going to cancel out, and I'm basically getting 76 divided by 32, and then it's times sine of 35 degrees. So I'm getting 1.36. 1.362 seconds. Now it didn't ask when will it reach the max height. That's what we just found. Okay, and I just did that with the normal parabola equation, negative b over 2a, right? From this thing right here, negative b over 2a is your maximum vertex input. The input of this particular equation was time, so that gave me the time that the maximum occurs. Okay, now the height naturally is going to be if I take this and plug it in. Right? Into y equals blah, 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 blah. Okie dokie. When I do that for this one, what I came out with was 36.2 feet. So at 1.362 seconds after the pass leaves his hand, it reaches a maximum height of 36.2 feet. Okay, and then lastly, how far away does it strike the ground, assuming there was no one there to catch it, right? Maybe it's a practice throw, who knows? So we want to know this maximum distance over here. Well, notice to calculate an x, I simply need to do 76 cosine of 35 degrees just times some amount of time. So what I really need is, at what time would it strike the ground? Okay? Well, it's going to strike the ground when the height is 0. So this is what I need to do. The time till it strikes the ground is when y equals 0. The height is 0. Right? So I'll do 0 equal to negative 16t squared plus 76 sine 35 degrees times t plus 6.5. This is just a quadratic, and as yucky as you might think it looks, this is one of the main reasons we have the quadratic formula, right? Because of situations like this where it's just a complete yuck monster of a quadratic to solve. Okay, so time is going to be equal to negative b plus or minus the square root of b squared, so 76 sine 35 degrees squared, minus 4 times a, which is negative 16, times c, which is 6.5, all over 2a. And what I want you to notice is that there's two answers here. And the reason for that is because the math is blind in this parabola. It thinks that the ball can go backward in time and strike the ground behind him before he threw it, which can't happen. So one of these two answers is going to be a crazy negative time number. The other won't be. It'll be a nice number. We can already tell which one that's going to be. Look, negative divided by negative, this is going to be positive, okay? And then if I do negative divided by negative again, that will also be positive, okay? But if you do positive divided by negative, it'll give you a very large negative number that will overtake the other piece, okay? So right here, instead of plus and minus, I'm really just going to take the minus. Okay, I'm getting that so that it matches here and here. All three of them are negative, guaranteed positive value. The other one must be the negative value. Okay, and when I plug all of that in, what I came out with was that this time is approximately 2.86623 seconds. Okay, so that's how long it took to do that. Now, how far away? What's the x distance? X is going to be 76 times the cosine of 35 degrees times the time. So I'll plug this in there. And then what will I get? Around 178.4 feet. Now, what was funny about this is how far away this is predicting that would be, right? Divide that by 3 and you get about 59 and a half yards, right? So basically right around 60 yards. I Googled this person on average, how far does one of his paths go? It said 60 yards. So again, this is by no means connected to any real, paths of any kind or saying anyone's performance one way or the other. I claim no stake in any of that, but I do stand by my math. And it is kind of cool that the beginning stats led to the same ending stat as the reality. So real quick, just wanted you to see what this looked like on a grid. I put in the x and the y functions of t exactly as we had them written on the board. And then I just wanted you to notice a few things. Notice the height does start right at the 6.5 mark right here. You can see it's at 6.5 on the y-axis. And I plugged in the maximum time value, my b value for the interval there, as the 2.86623 that we computed should be the time that it hits the ground. And you'll notice the parabola stops right there on the axis because that's the time when it's going to hit the ground. And of course I started my a at 0 because that's time equals 0. So if I hit play here, you can see this point does actually follow the path. Very linearly, in fact. The path isn't linear, but the speed is very linear. And right when I get it to the end of the path there, you can see it's hitting the ground, or it's trying to anyway. I don't have enough decimals on that thing for it to finish. But you get the point. Okay. Also, the when t equals 2, right, was one of our questions. So right here, or right about, right? And we said the height was 29.7. You can see it's right there just beneath the 30 mark, right? 29.7 when the time is 2. And then the maximum height occurred at 1.362 seconds. Close enough. As you can see, I put in 1.36 for my t, and it is actually at the very peak up there, and it has a height of just over 36, right around 36.2 feet in the air. I'd like to finish up with 3 more examples of how parametric equations really can take us to the next level while still talking about something that it can classify as a function. Okay, now 2 of these examples can only be done in parametric equations, at least, with some sanity. And then this first one here is kind of an either or, but really is a lot easier in parametric form. Okay, so here I have this where x is something squared and y is related to something cubed. Okay, and t can take on any value, obviously, because there's no restrictions on t there. So to sort of get an idea of what this would look like in the other form, I'm just going to go ahead and eliminate the parameter. To eliminate the parameter, I'm going to recognize two things. First, I'm going to recognize that x plus 1 is equal to t squared. Right? Then, using that fact, I'm going to say that y is equal to t times t squared minus 2, and therefore y squared is t squared times t squared minus 2 squared. So then y squared is equal to t squared is x plus 1, and t squared right here is also x plus 1, but minus 2 when squared. So my rectangular equation has this form right here. Y squared is equal to x plus 1 times x minus 1 quantity squared, which this side is no different than any other polynomial that you've looked at, but since it's equal to y squared, if you wanted to be an old school function, you would have to square root both sides and only take the positive one, okay? In which case you would lose half of your information. Let's look at a few values of t, x, and y here. Let's see, let's do -2, -1, 0, 1, and 2, as we have before. It's a very efficient way of doing things here. At -2, I'm gonna use this to calculate it up here because it won't be as much fun with this equation. Up here, when t is -2, notice I have 4 minus 1, which is 3. And that's the same thing for this one down here. Okay, and then y is going to be -8, because it's -2 cubed, -8 plus 4, right, which is -4. Okay, so at -1, x is going to be 1 minus 1, which is 0. That's going to go for the same thing here. And of course, this one will be -1. And y is 0 when t is 0. Okay, so then also, right here, -1 gives me -1 plus 2, which is 1. And this one will be -1. And then, of course, at 3, oh, I did this one wrong. My apologies. I was thinking I was plugging, oh no, I did do it right. Okay. Because I'm plugging in -2. Yeah. So 4 minus 8. And so here with plugging in the 2, that would be 8 minus 4, which is 4. Okay, yeah, so that's right. Yeah, because that's an odd function, that's an even function. They should have that kind of symmetry behind them there. Now here's something else that might be important. What if we wanted to know some x and y intercepts, right? Some x and y intercepts. The x-intercepts might be somewhat obvious to you because it's whatever makes this side 0, right? But it doesn't work that way with the y-intercept because I have other pieces to solve here. The y-intercept is not obvious from here, okay? However, I can see right here that I'm going to have, I'm sorry, I got those back. The y-intercept is when x is 0, so that's obvious. The x-intercept is not always what's obvious. I'm going to have an x-intercept when y is equal to 0. So it's actually easier to solve those on this end, right? Rather than trying to set the y equal to 0 and solving this equation, or vice versa, setting them all equal to it. Okay, so here y is going to be equal to 0. Then I'm going to solve right here when t is either 0, right? Because I'll factor this out into t times t squared minus 2, right? Either t is going to be 0 or t is going to be plus or minus square root of 2 when y is 0, right? So I have this one, right? T is 0 when y is 0. Now, notice I don't have the other one in here, right? When t is either plus or minus square root of 2, then I'm also going to get a value when that happens, right? Plus or minus square root of 2. I'm also going to put in my little chart here. My y value is going to be 0 when that happens, okay? But then what's the x value going to be? Square root of 2 squared, whether it's positive or negative, gives me 2, right? And so the x value is going to be 1. That one was not on a nice t value, but it was easy enough to solve. So let's see what kind of shape we're getting here. The shape is going to look like this. Like this, give or take some. Of course, this over here is at -1. This point here where it hits is also at 1. And then as you can see, the other two y value points are also at 1 and -1 for this particular curve, right? Okay, but what's important also is when are the t values occurring? T equals 0 is here. Right? This is t equals 0. T equal to 1 is at the 0, -1. This point right here is t equal to 1. So therefore the flow must be in this direction. Like this, right? It's doing this sort of spiral like this. Okay? Now what's cool about this one also that should be sort of questioning in your mind is that I'm crossing over the same point twice. And it was bad enough before when we had graphs that weren't passing the vertical line test and I'm still telling you these are functions. Okay? But now they're crossing over the same point. How can that still be a function, you say? We've got these repeated values that violates that definition. This is okay, because each and every single one of these points is a different t value. And that's why we can assign the flow, and that's why it's okay that it crosses over itself. Okay? This particular point is actually hit at 2 different times, 2 different t values. Therefore, it's okay. This whole entire thing can still be a function when it's in parametric form, because now our domain is dependent on the t variable, not any of the other variables. Okay? So right here, notice these two points right here, they occur at both plus and minus square root of 2 for a t value. Right? So t is negative on this top loop right here. And then t is positive for the upward spiral part this way. So it does cross over itself, but that's okay. All right? So look at, here's another one that sort of compounds that same idea. Earlier we looked at what happens when you change the frequency, and remember it played foogity with our theta interval, okay? But what if they're different angles? This is no longer something that I can easily collapse. And to be honest with you, this one would not be yummy or fun to convert into rectangular form. We've now moved into an example that in rectangular form would be pretty much untenable. You wouldn't want to touch it, you wouldn't want to have to analyze it, and yet in parametric form, so simple. But look at the curve that it generates, okay? The axes, by the way, on this one, my drawing's not perfect. I'll show you in GeoGebra in a second, but the axes go kind of like this, right here. But actually, this should be kind of up there, actually. But in any case, you see the way this goes. It's a curve that goes like this, and then curves around this way, and then back up this way, and then back onto itself, like that. What's happening is the frequencies being different, the y value is oscillating at one speed while the x is oscillating at another one. And so you're getting this mix-mash pattern, but by the time you get back to 2 pi, everything's going to repeat again. So it meets back up at the same initial point. And of course, if you increase these frequencies to even more, you have even more turns, and so on and so on. But this particular curve would be nonsense in rectangular form. But it does actually have purposes in some other applications when you may have waves coming from different directions, or different forces maybe oscillating things in different out of sync patterns. Okay? So curves like this can be very useful in studying all sorts of things, but only in parametric form. And here's a more simple application that works pretty much only in parametric. It's called a cycloid. Imagine a point on the very end of a wheel, and as that wheel turns, the point maps out a path. Okay? So imagine this blue wheel right here turning. Okay? This point is going to keep going up and then down, hit the ground, and then the wheel is going to keep going around and keep going around. You get what we call a cycloid. And this is actually just the most basic kind of cycloids. There are all different other kinds of cycloids. Epicycloids are where a wheel's on the outside of another wheel, or a hypercycloid where a wheel is inside of another wheel and turning around. All different sorts of patterns for things that we use in engineering all the time. Okay? But the only way to map out this point on the end of the wheel is first to generate the motion of the wheel. The center is going forward, right? Which is why you get the theta and the 1 right here, or basically the theta and the radius here of A. Okay? That's the motion of the wheel, just that theta and that 1 there moving forward. But then the sine theta and cosine theta come in to the fact that from the center, the sine and cosine generate the circular motion as it's moving forward like that, right? So it's got to go around as it goes forward. Hence I have to subtract off the sine and the cosine distance away from the center. Okay? And just that simple form in parametric gives me this complicated periodic function where the period is 2 pi a, whatever a is, right? And the max height is 2a. Okay? Notice that means that the radius of the wheel is a. Well, if you were to try and put this into rectangular form, just imagine, there's not a good way to square these, because then I would have to FOIL, and I would have theta times sine squared thetas and thetas times sines, and here I would have all sorts of other mixture cosines as well. So what if I just try to do it directly? Well, if I try to do it directly, this bottom equation becomes theta is equal to the inverse cosine of 1 minus y. Already starting to look yucky, right? Now imagine plugging that back into here, right? If I plug this back into here, what we would get is x is equal to arc cosine of 1 minus y minus sine of arc cosine of 1 minus y, which, by the way, if you look at my trig videos, you'll notice there is a way to actually simplify those kinds of things. Basically, we would get something with a 1 minus y squared in the inside of the square root. But this one is not simplifiable. And then we still have to be able to subtract those two quantities. It's just a real huge mess. I couldn't even imagine trying to graph that in a rectangular format. But in a parametric form, this is where a is equal to 1 right here, the one I picked. It would be a very easy task to see, oh, well, the radius of the wheel is 1, and then I can plug in some theta values and figure out like where the wheel is at some certain amount of time, right? Pick the position. It's very easy in parametric form. So things like this are really why you need to start building your parametric skills, because some things that you're going to study can only be put where your two different dimensions, your x dimension, your y dimension, can be described by some third party connecting variable, which is what parametric equations do. Go take a look at these real quick in GeoGebra. They look great, much better than I can draw them. And I hope this lecture has helped you get started on the huge path, pun intended, of curves in parametric form. All right, so finishing up here, we're going to look at these three more advanced examples. The cubic curve that we talked about first was this parametric equation right here. This was the equation that we converted it to in rectangular, and this right here is the equation that you would use if you were trying to turn it into an old school function. So notice the equation itself graphs to this, and it's even a little bit imperfect. Notice it's got this little gap right here. The parametric equation can actually clean that up. Watch as it draws right here. It's going to get straight through that center point, and then it's going to loop around and cross over itself right about here. See, it comes through, loops around, you can tell the direction of the flow, and then boom, it crosses over itself. And you can see that that's a much cleaner version. There's no gap. It's all exactly correct where it's supposed to be. And it is exactly the same as the equation, the other equation. Okay? Now, here's another thing to notice. If you do the function version, the old school function, notice this doesn't pass the vertical line test. Our old school function would. This is what would happen if you tried to do it in the normal old school function rectangular form. The graph would have this sort of crazy cusp even right here. See this sharp corner? Making it impossible to differentiate there at that point because it's a cusp. However, as we'll see in the next lecture, because of the way we can define this thing smoothly in parametric form, I will actually be able to find derivatives there, because there are two distinct different t values at the negative square root of 2 and at the positive square root of 2 when they cross over there. Okay, next we need to talk about the trigonometric one right here. And I tried my best to draw a by hand version on the board, but by no means did I do it justice. So here is the curve being drawn in normal. Oops, wrong one. That's the point. It's kind of cool to see the point move, but here's the curve. Now what's happening is one dimension has 3 cycles per loop, and the other one only has 2 cycles per loop. So it has to give each one its proper, cycling. And it ends up having to cross over itself quite a bit here, as you can see. Take careful note also that it never goes further out than the distance of 4 on these things. And that's because of the way sine and cosine work. Okay, so there's the full curve. And then you can tell also that the way I had it drawing was also the direction of the flow. This is the direction of the flow as a point would travel along the values of t. It looks even weirder when you don't have the curve there to show you that it is doing the correct path. But in real life, if something were actually following this motion, this is kind of what it would look like. And then you would come up with the path later. And lastly, we were talking about cycloids. Now a cycloid is going to be when we have the wheel here. And right now I'm doing a wheel of radius 1 to mimic the equations that I had on the board there. And then I'll show you what happens when we increase the radius. Okay, so here I'm going to start playing the curve here. Watch this point. This point right here at the bottom of the wheel is the one that we're actually following his trail, his path. So as the wheel turns, you can see that what's being drawn out is the path of him. Let me do it all again. Let me slow him down just a bit here so that you can see what's actually happening. Let's start over one more time. Is that point right there is following an up and down pattern of flowing on the wheel. And sometimes the point is moving, backwards of the forward motion of the wheel, and sometimes it's moving with the forward motion. Hence why you get the speed up and the slow down of the cycloid points. Also note that the first mark right here is just a little bit past 6. That's 6.28. or in other words 2 pi times 1. The radius of the wheel is 1 right now. So one period, one hump of this is one period of this function is going to be 2 pi times 1. Now, if I take my wheel here and increase the radius more, let's make it a radius of like 2.5, let's say. I may have to type it. Okay. Let me zoom out a little bit here. Try to keep the values. And then we play it. Notice the wheel is turning somewhat slower to your perspective, but it's covering a much wider arc, and then one loop gets a lot further. You can see that one loop, one cycle of this thing, is just shy of 16, which is going to be 2 pi times 2.5, right? So something a lot bigger than 2.5 times 6.28. So there we go right there. If you're interested in cycloids also, don't forget that there are other types, the hypocycloid and the epicycloid, all about wheels spinning inside and outside of other circles, and to give the patterns that fit inside of those things. Don't forget to try doing one of these cycloids yourself. Not necessarily with the wheel and everything. Notice the actual wheel doesn't even have to be there to make this cycloid work, right? The cycloid is going to be the actual, just the function that you have, that you see in front of you here. So it graphs out just fine. And GeoGebra is a good tool to use for trying these out yourself. So is Wolfram Alpha, so is Mathematica. I hope all of these parametric equations has broadened your perspective of functions, and I urge you to go try all of these out. They're actually very, very fun.